the volume in tank B is 2.21 cubic meter. So that one we can calculate using the ideal gas law.
I think I did it with a different formula. But
Yeah.
I got, I think, the same answer.
Yes?
But I don't know if I'm doing it right, because I used the PV is RT.
Yes.
It's also
Yeah. Yeah. Okay, now we have determined this. Now these two start to mix, and we end up with a mixture at a temperature of 20 degrees Celsius. And we know the total volume, so at the end, at equilibrium, the volume is 1 plus 2.21, that's 3.21 cubic meter. We know that the temperature is 20 degrees Celsius, and I need to know what the pressure is at equilibrium. So how can I determine that one? How can I determine the pressure after the two tanks have mixed? Again, we have pressure, temperature, and volume. So which equation?
I used the same one. I used
Yeah.
PV is MRT.
Yeah, that's correct. You can again use the ideal gas law. In this case, it's P times small v is RT. The only problem is we know the volume, we know the final temperature, but to determine the pressure, we have to know the specific volume, and we know the total volume, but we don't know the total mass. Because we calculated this for this tank, so this was all for tank B. This whole calculation was done for tank B. But yeah, if we want to know it for the total system, then we also need to know how much air was present in this one. So if we want to calculate the final pressure, we know the pressure, that's the one that we have to calculate. We can look up R in the table, it's the same one as with the first calculation, and we know the temperature, which is 293 Kelvin, it's 20 degrees Celsius. So we first need to know the specific volume, which is the total volume divided by the mass. And the total volume is 3.21 cubic meters, but the total mass is MA plus MB. And we know that the mass in B was 5 kilograms, but we do not know what the mass in tank A was. Shit, so we have to calculate that first before we can answer the question. Well, how can we calculate the mass in tank A? We have a volume, we have a temperature, and we have a pressure. So again, we can use the ideal gas law. So the pressure in A equals the specific volume in A times the gas constant for air and the temperature in A. We know the temperature, which is 298 Kelvin before we start the equilibration. We know the pressure at A at the beginning, which is 500 kilopascal, and we can find R value in the table, and then we can calculate the specific volume in tank A. And the specific volume in tank A equals the total volume of tank A divided by the mass of the air in tank A. And volume in tank A was 1 cubic meter. So in a roundabout way, and you use the other formula, but it amounts to the same thing.
But I think it's easier.
Is it?
Yeah, because now you're splitting up the formula into.
Yeah.
Of course, it's true because the specific volume is the volume divided by mass. But I don't know.
So you find it easier to use the volume? That's the one PV.
Is MRT. Because you have the mass there directly, you have the volume
Yeah.
directly, so you don't need to split it up.
Yeah. So this is the same formula, only you have instead of V, that's V divided by N.
Yeah.
Yeah. So it's more or less the same. Yeah. Maybe that makes it clearer. Yeah.
Because in the book they also used that one, and I tried. It's easier, I think.
Okay.
Because I get the same answer.
Yeah. So this is the way you have to solve it. I'm not going to do all the calculations, but first you have to calculate the pressure in tank B. Then you have to calculate how much kilogram of air you have in tank A. And then you can answer the second question, the final pressure in the whole system. Okay, next question. This was 13. Other ones? Okay. This is using the gas equation again. This is using the generalized compressibility chart. Specific volume using the steam tables. And this is the specific volume you have to know which one has the biggest difference compared to the one in the steam tables. That's the calculation using the gas law. The use of the tables is not a problem. You're able to find your answers there. The only problem is that sometimes you have temperatures or pressures that are not in the tables. And then you have to interpolate between two temperatures or two pressures. And that's not maybe very difficult, but it is a lot to do.
It's annoying.
Yeah, it's annoying. Correct. Okay, that was chapter 2. Chapter 3 is about closed systems, and it's about PV work, so we get lots more formulas where the pressure and the volume and the work that's being done if this changes is calculated. So closed systems are systems where there is no mass going in or going out, and then you had adiabatic processes. Those are processes where we have no heat transfer, so you could say they're more or less isolated thermally from the environment. And then you have systems that are completely closed, where no energy can be released and no work. Sorry. What was it again? I'm not sure, it's not here in these slides. I'll say no more about it. But adiabatic processes are processes where the amount of energy that's transferred between the system and its environment is zero. Now, we have a bit of a change here from the chemistry course. Here, if you add heat to the system, then Q is positive for the system, so that's normal. But in chemistry, you are always taught that if the system does work, if the system pushes away the atmosphere, for example, then you were taught that the energy that goes with that is negative. And here they do it the other way around. So they say that if the system performs work on its surroundings, then the sign convention for the work is positive. So that's different here from what you were taught in the chemistry class. So work going out, if the system performs work on the environment, we have a plus sign, and if the environment surroundings work on the system, then that work has a minus sign. Energy going out is negative, energy coming in is positive, or heat coming in and coming out. And then here you had these definitions of convection and stuff like that. I'm going to focus on the work. Heat, energy transfer associated with a force acting through a distance. So force times distance, sign convention, boundaries, mechanical forms of work. So if we move an object using a certain force over a certain distance, the work that we have is force times distance. If the force remains the same the whole time, that's an easy calculation. But it is possible that the force changes over the distance. And then it's not a straightforward calculation. You cannot do just F times total X. If the force changes during this road, you have to do an integration. Now, we are going to focus on boundary work, moving boundary work, gases expanding and contracting. The work associated with a moving boundary is called boundary work, which is force times the dx, the distance over which the piston or the system boundary is moved. And this is the change in volume. This surface area of the piston remains the same. So in that case, we can take the surface area of the piston out of this calculation. We can write the force is the pressure times the surface area. And surface area, this surface area times this height difference is the total volume change of this system. So we can write P times dV in this case. Now, if we have to integrate this, because the pressure doesn't remain the same during the whole process, for example, we have to do an integration for this calculation of the work. And if we want to be able to do this calculation, we need a relation between the pressure and the volume. That's the only way we can integrate it. So then you can use your maths course. The work can also be seen as the surface under the graph. So if we have a PV diagram for a certain process, then this surface area here equals the amount of work that's being done. And if we have a circular process, the amount of work that's being done is the surface area that is within these two graphs. This is the one road and this is the other road. And this area in between is the work that's being done by the system. Now, these are important equations to know. For an ideal gas, we can deduce, using the ideal gas state law, the following equations for boundary work. The work equals the mass of the gas times the specific gas constant times the temperature difference divided by 1 minus N. And that's for a gas where N is not 1. Where does the N come from? Oh yeah, this one. For polyprotic processes are processes that meet this equation, P times V to the power N equals a constant. And N and C are both constants in this case. Now, if n is 1, then the boundary work is P1 times V1 times the logarithm of the change in the pressure. And for an ideal gas at a constant pressure, this changes to boundary work as pressure times end volume minus initial volume. That's the easiest calculation. Let's see. First law of thermodynamics. Closed system, the net energy transfer from the system as heat and work equals the net increase and decrease in total energy of the system. See? Net energy transfer to or from the system as heat or work equals the net increase or decrease in the total energy of the system. Yes? So in equation this says heat exchange and work exchange is the total energy change in my system, is the energy going in minus the energy going out. And this can be either work or heat or both. Now, the total energy change can be related for most systems that we are discussing as the change in internal energy plus the change in kinetic energy plus the change in potential energy. And for stationary closed systems where there is no change in the center of gravity or in the velocity of the system, then the change in potential and kinetic energy are zero, and the first law becomes change in internal energy equals heat exchange and work. And that's one we are going to use most often, I think. Okay, you can use it as a unit mass base, so these are all specific changes in heat, specific work, specific internal energy, so that's in kilojoule per kilogram, or in differential form where it is related to, when you have very small changes, or in the rate form, so then it is also divided by a time used. For a cyclic process, initial and final states are identical, so the total energy change is zero. You can have an energy change if you go from here to here, and an energy change if you go from here to here, but these two energy changes will be equal to each other because if it arrives back at its original state, there's no change in energy. More important specific heats, Cp and Cv value. You have a specific heat at constant volume, specific heat at constant pressure. Let's see. We can also say Cv is the change in specific internal energy per unit change in temperature at constant volume. And Cp is the change in specific enthalpy at constant pressure. So if we have constant volume, Cv is related to internal energy, and if we have constant pressure, then Cp is related to the enthalpy. And we can also relate the enthalpy and the internal energy by this equation, lots of equations coming by. At a given temperature, internal energy, internal enthalpy, the specific heat at constant volume and the specific heat at constant pressure are constant, independent of pressure or specific volume. So at a certain temperature, these do not change, these specific characteristics. They only change with the temperature for ideal gases. For small temperature intervals, we can assume an average specific heat. So if we know specific heat here and we know it here, we can use the average specific heat between these two situations to do our calculations. And there are three ways of calculating a change in internal energy or a change in enthalpy using these specific heats, using the tabulated U and H data in tables, or using the specific heats as a function of temperature, or using average specific heats. They will come by in different questions. I'm not going to explain a lot about that now. I suppose we focus on the quiz from chapter 3. Which ones would you like to discuss? Which one? 4. During an expansion process, wait, first erase this question. Question 4. During the expansion process, the pressure of a gas, so we have an expansion. Let's assume we have some kind of cylinder where there's gas. And this is the initial volume, and then this starts to move up. This is the final volume. A gas changes from 100 to 900. The pressure of a gas changes from 100 to 900 kilopascal. So the initial pressure is 100 kilopascal. And the final pressure is 900 kilopascal. According to the relation, P is A times V plus B. So the relation between pressure and volume, A times V plus B. Where A is 1 megapascal per cubic meter, so this constant is 1 megapascal per cubic meter. And B is a constant, yeah. If the initial volume of the gas is 0.2 cubic meter, then the question is calculate the work during the process. So we need to know the boundary work. Well, if we have a constant pressure, then it's very easy. The work is P times delta V. But we don't have a constant pressure. As you can see here, the pressure changes with the volume. So in this case, my boundary work needs to be an integration. It's the integral from the initial state to the final state for P dV. That is what we have to calculate. Well, we have to do an integration here. I'm not sure whether your integrating skills are up to scratch, but instead of P dV, we can write A times V plus B dV. So we need to take the integral from the initial state to the final state for A times V plus B dV. And we can switch this as A times V dV plus B dV. Well, if we have V dV, does anybody remember what the primitive of V is? If you have X dx, maybe that's more familiar. You have to calculate the primitive of this one. What is it? Do you remember? From integration?
Long time ago.
Long time ago. It is. It's this is the primitive of this one is A times half V squared. That's the primitive of V dV. And if I just have a constant, then the primitive is BV. So these are the two primitives for this function. And during the exam, I will not ask you to find the primitive of the function. Okay? I promise that. We have to calculate this from the initial situation. So we have 0.2 cubic meter to the final situation, but we don't know yet what that is, I think. Do we? Yeah. Yeah, first we have to know what the final volume is if we want to be able to calculate this. We know the initial volume, but we don't know the final volume. The final volume can be calculated using this equation. We know that pressure equals A times V plus B, and we know that A is 1 megapascal per cubic meter, so that's 1,000 kilopascal per cubic meter. If we look at the initial situation, then we know that volume is 0.2 cubic meter. We know that the initial pressure is 100 kilopascal. So for the initial situation, we know that 1,000 kilopascal equals 1,000 kilopascal times the initial volume, that's 0.2 cubic meter, plus B. So for the initial situation, we just fill in the pressure and the volume and the constant A. And from this we can calculate constant B, which is minus 0.1 megapascal or minus 100 kilopascal. So now we know the value of B. Well, for my final situation, I know the pressure. So P final is 900 kilopascal equals 1,000 kilopascal times the final volume minus 100 kilopascal. So from this we can calculate the final volume using the relation between P and V, which is 1 cubic meter. If we fill in all these numbers. And then it's a question from filling in the final, so this is 1 cubic meter. volume and the original volume in this equation, like it is given here, you first have to fill in the final volume, V2, in this equation, using A and B and 1 cubic meter. And from that you subtract the value of this sum at the initial volume. Yeah, that's integration. It's difficult. So we get A times a half V2 squared plus B times V2 minus A times a half V1 squared plus B times V1. That's the answer to the question. But again, I will not let you do integrations at the exam. Okay, other question?
Last one?
Yeah, last one.
The last one.
Without integration.
Determine the enthalpy change of nitrogen in kilogram per kilojoule. First, I'll erase this again.
Maar is dit niet de goede? Is dit de laatste?
Oh, I'm not sure. I'll have a look.
It's about a distance in
Deze ook van...
No, it's not the last one, sorry. This is the last one.
deze. Ja.
We zitten hopen dat ze al weg zijn. We hebben nog een drie kwartier. A piston cylinder vise contains 0.8 kilograms of nitrogen. Question 14. .8 kilogram of nitrogen.